You can hear now. So
Yes.
this is Peter Baumann speaking. If you experience me as many times you did maybe with Jota, I suggest that we just all mute except for the one speaking so that we avoid all those echo. Thank you. Having me once is just enough, I guess. I still hear some echoes, so please everybody mute, but I will start over now so not to lose any time. So thanks a lot for joining in. I've heard that we are really a big crowd today, and I would like to talk to you about the concept of Datacubes as a new way to see our data and to make it easier to work with them.
We cannot hear you, Peter. Sorry, but we cannot hear you now.
Can you hear me now?
Now, yes, you're back.
Okay, I'm still getting an echo, but I still continue. Okay, so it's about me being a database guy that always likes to analyze the data structures behind. And whenever I look into that, be it science, different domains and faculties, or engineering, or business data, whatever, I actually find just a few basic data structures. So these randomly picked examples that you see, they cover stock trading, and we find sequences which can be mapped to arrays in a programming language sense. Social networks form graphs, ontologies as well, just smaller graphs. In climate modeling, we have something like 4-dimensional and even 5 dimensions, and so on. I don't want to go through all because
We have lost you again. We cannot hear you, no. Now you're back. Thank you.
okay. So this system tends to mute me randomly. I try to have a look at it, but that is interesting. So Adobe says don't talk so much. Let's come back to the structures. So we find things like which we can handle conveniently in relational databases. We find hierarchies where we have, for example, XML databases. We have general graphs that we can handle with graph database systems like Neo4j, or we look into Sparkle and RDF to model and query graphs. And then we have the arrays. So data that are structured along some dimensions. And actually, it's amazing how far you get with only these 4 data structures. And if you ask me now, so what does that mean in practice, having such arrays? Well, typically it is sensor data, or images, or image time series, or simulation output, or statistics data cubes. So if we look at what such a data cube means in a definition sense, then first of all, it's data that are aligned on some grid. Some people call that rasters. Programmers tend to call that an array. It can have any number of dimensions. So actually it's starting with one-dimensional pseudo-grids, actually, like time series, for example. Time series of temperatures measured in a river. The important thing is that these sets of elements that we find, all these data are ordered in some abstract space, in some Euclidean space, along their coordinates. The cells themselves, single or composite cell values, whatever, but it's important that in such a data cube or in an array, the values all are of the same type. That makes it much easier to handle them. The nice thing is, if we take a vector, then this can represent an address in the data cube. Sure, we understand that. But actually, if we address such array element, we can compute its address. We know the mapping scheme, so actually we do not need to store the coordinates, which makes it a very efficient representation. So for a d-dimensional array, you would have a vector of length d. Now, as for the terminology, for each dimension or axis, we have a lower and upper bound. And inside that, we have cells containing cell values, and the environment, the surrounding, we call the spatial domain. So that is the area where we find mean values. Sometimes it's called bounding box, and I've even found the term shape for it. So that is the abstract definition. You may wonder now, where are my geo-coordinates? If I'm looking at Earth, I need to have latitude, longitude. Well, actually, first of all, we have integer coordinates by enumerating the cells along their dimension axis. But we can ornament such a data cube, and we can define a mapping that gets us from latitude, longitude to I and j index coordinates. This way we have a nice separation of concerns. On the one hand, we have the pure data cube. On the other hand, we have all the gory details of modeling space and time coordinates and whatnot. Now, if we want to store them, actually we have different ways of doing that. Traditionally, you would put that into a database blob or into some image file. So you take a two-dimensional matrix, you linearize it, and that's what you store on disk. A problem here is, if you look into your image that we have here with the O's and the X's, then we find a very well-defined area, the red axis, which is a subset which we may want to extract. On disk, however, our linearization destroys that nice neighborhood relationship, and so we have to jump from the first line to the second line to the third line and so on. This is expensive because your diskette needs to jump from one position to another, and so it takes a long time to extract such subsets. Actually, it's even worse, because in the end you will compress your data and then you cannot compute any longer where your pixels sit. So the costs are very much depending on the dimension along which you want to access. Then some people said, okay, so then let's just enumerate the coordinates explicit, and we store our values together with the coordinates, and that's exactly what you do in relational OLAP, for example. Now, you may find that inefficient, but that's only the case for dense data. If you have very sparse data, so only very, very few values in this big space, then actually it's a very efficient compression technique because it avoids materializing all the empty space. Bottom line, our costs here are not position correlated. Along any dimension we can go with the same cost, but they are pretty high because we have to find tuple per tuple on our disk. So why not combine the best of both worlds? So we are fast and compact at the same time. This is actually what imaging is doing since the last millennium. They partition images into sub-images called tiles or chunks or partitions and store them together with an index to find what they need. If we have regular tiling, actually don't even need to store an index. So on a micro level, we have our coordinate-free sequence. Inside one such tile, we just can address, and hey, this thing is small enough that we can work on it efficiently, so we don't need to hop over the disk. On macro level, we have the enumeration of the coordinates because we remember the bounding boxes, and so we can find quickly which tiles we need for answering a analytics request. So what we get is, we get low costs for bulk access, for getting many pixels, and it's not location correlated, at least usually not, and it's also not location dependent. Therefore, this is a common approach that is being used in imaging, but also in multidimensional OLAP. In MOLAP, you find the same approach. This actually leads us to the analysis of such arrays, and so we can define array analytics as the efficient analysis of large multidimensional arrays, so meaning several orders of magnitude above the evaluation engine's memory. The evaluation engine, in our case, would be a server, and you may say, okay, I have a terabyte of main memory, fine, and then I say, and I have a petabyte array. So in our days, the arrays typically tend to be larger than what we have available in main memory. It means we need to care about disk management. Again, the essential data property actually is this n-dimensional Euclidean neighborhood. The red pixel has a very well-defined neighborhood of blue pixels, which can be accessed by simply varying the coordinate by 1. Secondary criteria can be something like the number of dimensions our Datacube has, or the density, or other data values. But this is just secondary. When it comes to operations, on a very high level, we could say it's linear algebra plus a few more items, in particular iteration, what we need. So we will have something like matrix operations, yes, but we have other stuff as well that we know very well from image processing and signal processing. So let's proceed, and now my slide is hanging here. I'm trying to get forward. Yes, because this should show you an example of how we have been dealing with such kind of raster data or gridded data in the past. We have split them, yes, and so we had a huge number of very small files that each one contained one such tile or partition. Maybe we have ancillary information, and because we want to be compact, we encode some information into the file names and directory names even. This is the classical case where you come with FTP and then you get lost, and after 2 weeks you hopefully manage to find what you really need. So let's step back and say, what if we don't need to look at, what if we had one single data cube per satellite instrument, for example? Okay, that's a really big thing then, and we need to manage that somehow. But so what? That is a task for the machine. We as users suddenly have a small number of objects, data cubes. We can slice and dice them, we can combine them, and so it's much more convenient. Incidentally, as it turns out, it's also more convenient for machines and APIs to craft. So that is the idea of the data cube, having one-dimensional cubes with space and or time dimensions, or even dimensions that do not adhere to space or time at all. And in the end, for a user perspective, it's just about this quality. I want a way to get simple access to those data that are sitting in a big data center, and I want to make use of it. This has been recognized even by the database community, you may say, although we have done separate silos since long. Metadata, yes, metadata can go into tables, but the pixel data, they go into several handcrafted solutions. And nobody would actually use a relational database today for storing petabytes of climate data, for example. But actually, SQL is advancing in direction. There is a draft of a standard which is going to become part 15 of the SQL language, called multidimensional arrays, in short MDA. You see an example below where there is a table definition. As usual, you have an ID and an acquired attribute. That is just as always, small data. And then there is a scene, so a satellite image, which actually happens to be an MD, a multidimensional array of extent 5000 by 5000 in this case. So we have told our database system that in these tuples we carry along large arrays. That enables actually to do operations on them. And so you see red operations in the select clause, in this case a band ratio, which is something that remote sensing experts like to do. And likewise in the where clause, you find operations that are embedded in SQL. This actually gives us a very high-level declarative language that is nice to use and that you can optimize on the server. But that's not all. Actually, what we have achieved here is that for the first time, we have red and green queries in the same query. What does that mean? Well, the green parts are metadata, the red parts are data. So in one and the same query we can combine metadata queries and data queries, and that effectively abandons this age-old subdivision between data and metadata. It's all just one common information space. So in this respect, this standard, I believe, will become a game changer for not only scientific data management. Now, we have looked at the concepts. Let me introduce a particular system on which we happen to work. It goes by the strange name of Rastaman, which actually stands for Raster Data Manager. This is something that we are doing now since about 20 years. And the idea is simple, and it is the one that I showed earlier. SQL is nicely flexible, and it allows for scalability on the server, but it does not support ND arrays. So if that's the issue we said, then let's integrate. And let's marry kind of an image and signal processing and statistics language into SQL. Behind the curtain, we have established a scalable parallel architecture that is based on peer-to-peer evaluation of queries and based on a principle called tile streaming. As I said, we are doing this since some time, so the system runs, it's in operational use, and we have databases exceeding 250 terabyte. And on OSGeo Live, you find Rastaman Community, the open source edition, as they say, particularly recommendable open source geotool. Also, the European Space Agency is convinced about that, and a few others that awarded us with some acknowledgements, as you can see at the bottom. But let's get further. We wanted to see technology. So, one example that shows us very much how this works, how to use SQL now for pixel data, that traces back to the time when graphics people told me, did you know, if you take a P image and put into the alpha channel elevation data instead of transparency, then WebGL in a browser can render this in 3D and you get a landscape that you can travel nicely. Cool, we said. That is something that we can generate. So here's a sample query. We take a red, green, blue channel and feed it with bands 7, 5, and 0 randomly from some satellite image. In the alpha channel, you find the elevation data. This actually needs to be scaled so that resolution matches. And the whole thing gets encoded as a PNG image and shipped to the client. In the background, you see an actual rendering of such a scene that has been generated via a database query. So among others, you can utilize that really to generate visual representations of your data. Of course, elevation doesn't have to be elevation, it can be population density or whatever. If you drive that further, for those of you who are interested in how far does it go, you actually can go into linear algebra. Not any operation, we are still working on ignoring that space, but you can do, for example, matrix multiplication in the query language, you can do histograms and other things. So you combine the operators and you get something that pretty much resembles the mathematical formula, so it's a relatively straightforward formulation. If that's not enough for you, then there is a concept of user-defined functions that is existing since long in standard databases that allows you to inject your own code. That is external code that is dynamically linked into the server. In Rastaman, we utilize actually the same API as for clients and generate some adapter code automatically to make it easier to use. And that is internally all integrated with tile management, parallelization, etc., which I will show in a minute. Here is an example that is actually taken from satellite image analysis. People sometimes don't trust all these fancy algorithms that produce level 2 products. They want to work on the raw data. Okay, so we take a Landsat raw array, and in there we pick an image and we do a vegetation index computation. Red minus near infrared over red plus near infrared. And we do so over a particular area. The result that has been processed on the raw data is fed into Orfeo Toolbox, concretely speaking its auto-rectification filter. So we get something that looks nice on a map, and the whole thing gets encoded in PNG again and shipped to the client. So the Orfeo Toolbox operations naturally become available as part of the query language, and you don't get any break here. You can pass on data smoothly. Okay, stop. Wait a moment here. I am not trying to sell SQL as the new general language that everybody should learn. We databases have understood that, although initially we called structured English query language. No, SQL for sure is not meant for end users or for developers of algorithms. Rather, it's a convenient interface between client and server. Just the same way we do it today when we build web applications that have a database underneath. Nobody sees the SQL. What you see is your well-known tools. And so actually, a goal is that interfaces really are the ones that people know already in their domain, and they can work transparently with a database behind. Today we can do that for Java and C++, Python, R is under work currently. You can use visual clients like NASA Whirlwind, for example. And the good thing is that standards are our friend here, because any client that exists that knows about these interfaces can attach itself to such a Datacube service and can fetch data. Such Datacube interface standards exist in OGC, they also exist in ISO to an increasing degree, and they exist in Inspire, for example. I'm sorry, I'm talking very much about GeoWorld here because this is the one where we are moving very much. But I believe the concepts translate into other domains as well. You can do similar things with confocal microscopy or with astrophysical modeling of galaxy clusters. So this is things that we have done already and which can be mapped to Datacubes as well. Now let's look a little bit behind the curtain. We had an initial glance at that and said, okay, likely we will want to partition our data. Actually, everybody does that today. We have studied that, and there was some interesting work by Paula Furtado, a former PhD student of mine. She has published a classification of tiling schemes, where we start with something very regular on the left-hand side, and go more and more arbitrary and random as we proceed to the right-hand side, up to the case where we don't partitioning that covers everything naturally, but where we say, hey, we have some areas that are of particular interest, our hotspot, and for the rest, dear system, do some partitioning on yourself. Allows us, for example, to do a partitioning that is good for time series analysis. Look at the yellow cube in the middle. If you assume that the time axis is going from front to back, then actually such a data structuring allows you to access all data pertaining to a time series very quickly. This is something that NASA has done, and they call it data rods. And on our side, this is one particular tiling scheme which can be modified at will. For example, you can have larger or smaller bricks and stuff like that. You may say that this is overkill. Very simple tiling is sufficient. But let's look at OpenStreetMap. You find a picture of the tiling scheme of OpenStreetMap bottom left. Now this is vector tiling, so not exactly the same, but they do share the problem of tile and how to design their tiles. And it's very clear that in downtown New York, we will want to have a very fine-grained resolution, whereas in the Southern Pacific, we maybe can put everything into one single blue tile. On the right-hand side, you see a picture showing a simulation of a pair of neutron stars rotating around each other, and we can nicely observe the varying resolution that is enhanced in places where we want to know the details particularly well. In other words, adaptive grids. So adaptive partitioning makes really sense for data storage of cubes. Now, when we come to processing, it's naturally that we say, well, we have several partitions, let's give each partition to one core, and then actually we can have a nicely, actually embarrassing parallelization, as it's sometimes called, because it just parallelizes so nicely. Well, on principle, there are some difficulties hidden, but first of all, it's nice to have a distribution scheme. The question is, what do we do with it? Do we fetch data once we have distributed them? That is not our approach. If some query comes and addresses data sitting in different places, we analyze the query and we find out that, okay, data set A is right with our core, with our node, we can process that immediately. Data set B is close by in the cloud or cluster, okay, that is no problem to access. However, we don't want to access it. We rather want to find a subquery that we can send to the node hosting dataset B. So that's the orange one. This becomes even more important when we go to the blue house, dataset C, when we are accessing data sitting in another data center. Then we definitely do not want to load Datacubes. We do not even want to download tiles. No, we want to send some processing to just get back the result. That is something that we do with every incoming query. We analyze it individually and find an optimization. Currently, our criteria are, number one, where do the data sit? And number two, how can we minimize transport along the red lines? This is just naive and brute force, if you will. So there is many more to investigate. That is ongoing research work. By the way, dataset D, we can go to moving objects and to moving servers. This is not a dream, but this is what we are going to do this year because Rastaman has been accepted as an onboard experiment for putting an instance on board a satellite and making it part of such a federation. That's something that we all like very much. We are really excited about that. The overall architecture that we find with such an array server is, in the end, we have some processing engine, which typically is multi-parallel. In the case of Rastaman, it's the RDA, as we call it. Doesn't have a single point of failure. It's a peer-to-peer organization. Notably, this is always neutral of any application domain. It's just bare arrays. The specific semantics comes in via extra layers, application layers. In this case, for example, geoservices that adhere to the OGC standards and know about regular and irregular grid. Underneath, of course, data could be stored inside a database, and that is how we started, and which is still something that is worth doing. So, for example, pixels can be stored in PostgreSQL. However, people approached us and said, well, we don't want to have extra database. Can't we use Rastaman standalone? So we implemented a file system solution that is round about 2 times faster than database because it omits some overhead of extra functionality that a database offers but is not useful in this context. So there's a choice. No, said data centers. Forget about this. Forget about copying 100 terabyte into the database. We cannot import data because this is just too much space. So, okay, I see something is missing on this slide because there should be an extra leg saying that there is substantial work, for example, by Anastasia Ailamaki in Switzerland, Lausanne, and others and ourselves are working on this as well. And today, actually, we can access any archive. Just tell us your archive structure. We'll only register the files, but not copy them, and then do query processing directly in situ on these old archives that exist. Always you have the same view. You send a query and you get an answer. This kind of peer-to-peer federation I would like to show you quickly. I have an example here where you see a query in the gray box, which is mighty complex, and in fact I couldn't explain it. It has been designed by a climate expert. But if you look into the from clause, you find that we want to use precipitation and Landsat 8 data. Altogether, this determines heavy rainfall risk areas. And as we are going to use precipitation data, why not go to the European Center for Medium Range Weather Forecast? They have such data. And so actually, they can do the query processing. So here is what's going to happen. Actually, ECMWF receives our query from Bremen, processes it, but finds out, oops, I don't have the Landsat data. However, it knows where Landsat data can be obtained, and that is National Computational Infrastructure Australia. So actually they send a subquery to Canberra. They gladly process the satellite data, and the result comes back, gets integrated, and you see it displayed, in this case, in a virtual globe. Now let's try to get rid of those, because actually we could likewise send the query to NCI. Now NCI will gladly process that data, and they will find out that they actually don't have the precipitation data, so they send a request to ECMWF in Reading, close to London. The guys do the processing there, send the result that gets integrated, and the whole thing is shipped back to us and will hopefully look the same as before. And here we go. Here's our rainfall risk classification that has been color-coded and provided with some transparency. What you in the end can see here nicely is, and this is why we established this demonstration, how queries get split automatically. You don't need to think about where the data are. You just send your query to one of the nodes in the federation, and they will sort it out by themselves. So coming back to the architecture, we can advance here. When I'm saying array databases, this is actually a whole category of systems today, and it's a well-established research area in databases. We have started that, as I said, quite some time ago. Then there were similar approaches to do that, which typically were tied to some thesis work. So after the student left, the whole thing was abandoned, unfortunately. And then we have an increasing number of systems that still exist and that are being developed. So you may have heard about SciDB. Then we have Oracle GeoRaster. They have tried it since some longer time. PostGIS, Raster, you may have heard about, etc. So this is a well-established research area, and there is technology available today. Talking about technology. Of course, when we talk about big data, then the next thing is that somebody says, oh, MapReduce. Now, MapReduce is an excellent paradigm for set-oriented data, but MapReduce does not know about the structure. It is not trimmed, it's not tuned for large-scale arrays. So if I have a red pixel here, I will very likely need the blue pixels in the next moment. As long as these pixels sit in the same Hadoop node, it's not a problem. But once they sit in different nodes, you all have to develop that yourself, because Hadoop doesn't know about it. So all the spatial temporal subsetting will be difficult. That actually has been investigated by benchmarks done by University of Wisconsin-Madison and George Mason University. It has been presented at HU in San Francisco 2015. And in the bottom right, you see the diagrams that show indeed Hive was faster than Rastaman for access of single pixels. Whenever you go into areas, you want to do computation, aggregation, or so on. So whenever you extract more than just one pixel, then actually Hive and also Spark are substantially slower. Okay, just on the side. Michael Stonebreaker has made a good observation here by just saying one size does not fit all. Remember the initial categorization into sets, hierarchies, and graphs and arrays? It's just that you need the right tool for the right task. Always the same. Now, if we put that together, let me present you the EarthServer Initiative, which is a large-scale initiative utilizing Raster Data. And actually what we are doing here is establishing agile analytics on three-dimensional image time series, so XYT, and 4-dimensional climate data, so XYZT. We are doing this on Earth and planetary data. On server side, we use Rastaman, and on client side, we like to use NASA Whirlwind. That is something where we have had our first phase, EarthServer 1, that was 3 years. Now we are in the second one. In the first phase, we went beyond the 100 terabyte barrier, and now we are approaching a petabyte barrier, standing at something above 250 terabyte at the largest installation currently. So you find Sentinel satellite data of the European Space Agency. You find Plymouth Marine Laboratory doing ocean color analysis, National Computational Infrastructure Australia hosting Landsat 8 data, and the European Centre for Medium Range Weather Forecast hosting the world's largest climate data archive, which is well beyond today. NCI and ECMWF you have seen in action when doing a combined fusion data query, and this actually goes towards the global data federation that we are heading for, so that you can access, extract, aggregate, and combine data cubes regardless of their size. And by the way, client-server interfaces strictly based on open standards. This is one of the domains investigated. I mentioned it earlier. We have looked into different ones. We have looked into earth sciences, so environmental, solid earth, seafloor, so ocean modeling, climate modeling, etc. In life science, we have looked into gene expression simulation and human brain imaging. And we have also put our nose into further stuff like computational fluid dynamics, astrophysics, or general statistics. So the interesting thing is that we have an overarching paradigm that actually can be used in an advantageous manner in many different domains. In other words, it's some horizontal platform technology. And this is not only good because it makes application development easier, but now we suddenly can combine data across different domains in one and the same way, and we can do a data fusion across domains. But once again, let me emphasize that the query language is not meant for the end user. They would likely do that with Python or with some visual client. Talking about standards, the standards world actually is very exciting these days. When we talk about geodata, we have the Open Geospatial Consortium, OGC, maintaining standards for location-based data. Here we find the concept of coverages, which includes multidimensional regular and irregular grids, and the Web Coverage Service. That's a suite of standards that allows processing, retrieval of data cubes and parts thereof. Rastaman, by the way, happens to be reference implementation there. And this is also being paired now in ISO. ISO had an old standard on an abstract one on coverages, which is number 19123. That is currently being revised, and it will become 19123-1, the abstract standard. And the concrete counterpart, the twin 19123-2, will be the OGC coverages standard. So these fit together. Independently, in a completely different corner of ISO, we find SQL MDA, the extension to the SQL query language with arrays. Inspire, for those of you who are familiar with it, the European initiative towards a common spatial framework, spatial data infrastructure in Europe. They also have adopted coverages and WCS. And they have adopted the reference implementation. This is where we stand today. I wanted to give a very quick overview on what this technology can do and how it works behind the curtain. This is by far not the end. This research that is being pursued by groups all over the world today is something that has lots and lots of open questions, and as usual, more open questions arise as we go. For example, we showed a distributed demo, which is natural because Landsat 8 is in Australia and precipitation data are in Reading. Fine. But what about active data placement? We could think about queries that get supported by shifting around data actively. Sometimes this can be faster. A next item is, okay, array database can handle arrays but nothing else. However, we want to have mixed data today. In database world, that is called polystores, which is a research direction that tries to integrate different models under a common umbrella so that people can combine all the different structures in their queries. Talking about queries, what about very complex access patterns that we have, in particular when we go into complex linear algebra operations? Or looking at the data, compression, yes, in Rastaman we can do compression, but hey, there is still more questions that pop up when talking about sparse arrays, for example. General linear algebra still has many operations that are exciting, and of course, applications. It's just fascinating, if I may say now, from a personal perspective, it's fascinating for a computer scientist to go into these domains, work with domain experts, and find solutions that work. So, as some colleague of mine said, let's put our pretty little minds together. And that gets me to the conclusion. I wanted to motivate that Datacubes, technically called arrays, actually form a major category of our big data, as we call it today. And array databases are a technology approach that strives to provide flexibility, any query, anytime, and scalability, so on any volume, on any size. We happen to have a standard that is emerging, SQL MDA. It's expected that the standard will be adopted this summer and become an IS, an international standard. It allows array querying, and it allows, as such, as a side effect, integration of data and metadata into a common information space. And this is something where many domains will benefit. So by several people, this has been called a game changer meantime. As an example, I use the Rastaman engine, which is geared towards flexible, scalable array queries. As such, it has served as the blueprint for several big data standards. It's also a reference implementation. If you want to know more, there is a link to EarthServer, the Geo Initiative, the Rastaman open source array source code, and about our research group at Jacobs University. And with that one, let me close with a thought. If we put together everything into one cube, then one cube definitely says more than a million images. Thank you very much for bearing with me.